Today we plan to discuss one of the most intriguing debates that went on for about 10 years from 1997-98 to about 2008 in the field of excited state processes, excited state dynamics. The reason why this is very close to my heart is that it started when I was a PhD student and I was working in proton transfer. So, and we could see that something interesting is breaking out. And the two groups involved, one were of Tahitahara, who was in Institute of Molecular Sciences, Japan at that time. Later on, he moved to Riken. And the other group was Amit Zoel's group. And this thing started in about 1995, 96, 97, when all of us could clearly see that Amit Zoel is going to get the Nobel Prize. So, a potential Nobel laureate, and on the other hand, we have a 33-year-old Japanese researcher led group, somebody who at that time did not was not confident in speaking English, never went out of Japan. So, that was almost a battle of David and Goliath, and at the risk of giving a spoiler, in the story in Bible, Goliath won. That is what often happens in real life as well. But it is not really an issue of winning or losing. This debate actually teaches us several interesting things. Maybe we will come to that at the end of this discussion. This discussion is expected to span 2 modules. Before getting into this debate of 7-aza-indole dimer, let me first present something else that also comes from the group of Tahitahara, more or less in late 90s. So, all of us know Kasha's rule, and all of us know that the reason why this emission spectrum is expected to be a mirror image of absorption spectrum is when we draw Jablonski diagram, this is what we always draw, that this is S0, let us say this is S2, there can be many more of course, and let us say this is S1, different vibrational states of S1. What we have learned is that you excite no matter where, you can excite to S2, you can excite to a higher vibrational level of S1. There is always ultra fast vibrational relaxation to V dash equal to 0, the lowest vibrational state of S equal to 1, and that is where the emission takes place from. So, this is the 0 dash 0 transition. You can have things like 0 dash to 1 transition, you can have something like 0 dash to 2 and so on and so forth. And while exciting, you can excite 0 0 dash and you can excite to higher levels as well. So, we are very familiar with this kind of a picture where this is the absorption spectrum, energy decreases this way. So, wavelength increases this way, and this is the emission spectrum. And we, as we have said earlier, this is what we expect to see for well behaved molecules. Of course, the entire business that we have is about molecules that are not well behaved, because if all fluorescence spectra are mirror images of absorption spectrum, then there is not much you can do about it anyway. So, when we have excited state processes, we get this red shifted band somewhere here. So, this is the mirror image spectrum, and this is the spectrum from that arises from the excited state process. I will just write ESP. Now, the reason why you do not get emission from S2 usually is that if I draw not like this, but in a little different way, if I draw potential energy surfaces, then generally this is the case. This is S0, this is S1, this is S2, this is S3 and so on and so forth. Of course, relative position of minima can be different. What we want to highlight more is that there is an energy gap between S0 and S1 generally, and generally S1, S2, S3, these three are not only close in energy, but generally there is crossing of the potential energy surfaces. That crossing can be adiabatic, non-adiabatic, that is a different question. So, since energy gap is small, it is very easy for non-radiative processes to happen among all these excited SN states, and S1 is the lowest energy state. There is a big energy gap. So, according to energy gap law, V dash equal to 0 of S1, that is where the molecule can reside for a while, and that is when fluorescence gets a chance. This is the very premise of Kasha's rule, and we have already seen how Kasha's rule can be violated if excited state processes are formed, are there, then you get red shifted spectrum. Now, we go to the other end of the story. Is it possible in any way to get emission from S2 or S3? And there is this very famous example that most of us might know, and that is of azulene. So, that used to be referred to for a long time as the azulene anomaly. In azulene, the major fluorescence is from S2 to S0. Why? That is because for azulene, I will just draw it here, the energy diagram is like this, this is S0, S1 actually has an overlap with S0, and there is a big S1, S2 gap. This is the conventional picture that has been known for 50-60 years now. So, that is why if you excite to S1, non-radiative processes take over. If you excite to S2, then only you can get some emission. So, azulene has an emission band that is at a higher energy than the lowest energy absorption band, because lowest energy absorption band of course is S0 to S1. Emission in this case is S2 to S0. Okay. So, this is something that is known classically. Now, Tahara's group had tried to ask the question, what happens in very short times? Is it that S2 is really non fluorescent, no fluorescence takes place, or is it that the lifetime is so small that you do not see the fluorescence in the steady state spectrum? So, the question is this, is it possible, and now I will draw only 3 lines to make things simple, S0, S1, S2. So, you excite to S1, you get fluorescence and you get some non-radiative processes, understood. Excite to S2, what is believed is this non-radiative process takes over, okay, and there can be some non-radiative process between S2 and S0 as well. But suppose for the sake of argument, we say that there is emission for S2 from S2 as well. First of all, where will that emission come? Higher energy or lower energy compared to the S1 emission? Naturally higher energy. Yeah. Now, the problem is this, we have discussed this multi-exponential model of fitting fluorescence decays, right. So, this is the most popular model where we fit like this, I at time t equal to I at time 0 sum over I a I e to the power minus t by tau I. Yeah, and steady state intensity, and now I will write lambda also at some particular lambda, or better write frequency, because there is a conversion factor between frequency and lambda, at some frequency is equal to integral of I nu at t dt. Yeah. So, this turns out to be sum over a I tau I, and then what we know is that if there are several components, then the contribution to steady state intensity of the ith component is given by a I tau I divided by sum over I a I tau I. I believe this all this we have discussed. Now, see, suppose I have a 2 exponential decay by exponential decay, tau 1 is something like 0.1 picosecond, and I will exaggerate just to bring out the fact, tau 2 let us say is 10 nanosecond, okay, and let us say they contribute 50-50, AI is 0.5, sorry A1 is 0.5 and A2 is also 0.5. What will be the contribution of this tau 1 species associated with tau 1, what will be the contribution to the steady state intensity? 0.5 multiplied by, so I can write like this, ISS of 1 will be 0.5 multiplied by 0.1 if I write in picosecond divided by 0.5 multiplied by 0.1 plus 10 nanosecond means how much? 10,000 picoseconds, right. So, 10 to the power 4. So, what will you do? You are going to neglect this 0.1 with respect to 10 to the power 4 naturally. So, in the numerator you have 0.05, yeah. In the denominator you have 0.5 into 10 to the power 4. What is the answer? 10 to the power minus 5. It is really very small. Yeah. So, the point is, if you have emission from a higher energy state that is short lived, then you will not see it in steady state. Is the point made? Yeah. Where will it be seen? Is there any way of seeing it? There is a way of seeing it, and the only way of seeing it is by using ultrafast dynamics. We have discussed already. Let us say this is your emission spectrum, steady state. Yeah, this is steady state. X axis let us write is let us write frequency. Let us be consistent. But then I should have perhaps written drawing it the other way. Anyway, y axis is intensity. Let us say I have two components, like one like this, one like this. This is the 0.1 picosecond component, and this is the 10 nanosecond component. Suppose I look at the time resolved emission spectrum, which we have discussed earlier, and suppose we look at the spectrum at time t equal to something like 0.2 picosecond. Will you agree with me that that spectrum at initial times, very short time after excitation, will be dominated by this species that has a lifetime of 0.1 picosecond? So, that is one way in which you can actually see a spectrum that is elusive in steady state, right. So, this is what mainly Takeuchi and Tahara had done prior to this debate actually. So, what they had done is they had taken some molecules and they had demonstrated that you can actually see the S2 spectrum. I encourage you to find those papers and read them. Right, in our presentation we are not going to talk about them, but what Takeuchi and Tahara had done before the 7-aza indole debate broke out was that they could actually demonstrate that you can see fluorescence from the S2 state at very small times after excitation. Okay. That is the background we need before we can get into the discussion. So, we are not saying Kasha's rule is wrong. We are not saying that Jablonski diagram we had drawn is wrong. All we are saying is that you can hold strictly only when you do steady state spectroscopy. When you do time resolved spectroscopy, then you can actually see things that are relaxing in very fast time scale and therefore, are not observed in steady state spectroscopy. Similarly, if you go down further to attosecond, which is now the state of the art, then you can see things that we assume even now in femtosecond time scale to be instantaneous. Almost nothing is instantaneous anymore. Okay. So, the take home message from this is you can actually see fluorescence from a higher energy excited state if you look at small times post excitation. Now, we get back to the debate and see how this concept turned out to be critical in this discussion. Okay. So, we will talk about excited state reaction dynamics in nonpolar solvents manifested by excited state double proton transfer of 7-aza-indole dimer. Mainly we will discuss these papers, there are many more as I am going to show you. We are actually presenting almost only one side of the debate, we are not presenting the other side. So, I encourage you to read everything, it is an engrossing debate. Now, I must thank Professor Tahi Tahara for sharing the slides with me, that first of all you almost if not here see it from the horse's perspective, and it also saved me a lot of time. I did not have to prepare the slides myself. So, 7-aza-indole dimer is a widely popular model for DNA base pairs, because if you just look at the dimer, it will remind you of how AT, GC are there in a DNA. Okay. So, you have two kinds of nitrogens here, one in a 5-membered ring, one in a 6-membered ring. You have two kinds of nitrogen, and the hydrogen is covalently bonded to the nitrogen in the 5-membered ring in both the cases. Okay. So, this is where I used to get confused, that why is it going from a nitrogen to nitrogen. Please be very clear about that, the two nitrogens are not equivalent. One is in a 5-membered ring, one is in a 6-membered ring, their acidities, basicities are different. So, in ground state, the proton is covalently bonded to this 5-membered ring nitrogen and hydrogen bonded to the 6-membered ring nitrogen of the neighbor, of the partner, and that is true in the other end as well. What is the symmetry of this system? What is the point group? Do we have a point of inversion? Point? No. Point of inversion? Yes or no? Actually, we do. We do, actually we do. Dimer, I am talking about the dimer, not the monomer. Point of inversion is there actually, but that hardly matters when we are trying to determine the point group, unless nothing else is there. Do we have a principal axis of symmetry in the dimer? We have a C2 axis, right, perpendicular to the plane. Do we have a horizontal plane, right? So, that makes it C2H. Do we have perpendicular C2 axis? Perpendicular C2 axis? One is there? No, nothing is there. There is no perpendicular C2 axis actually, because you cannot draw a C2 axis in maybe you are thinking of this nitrogen, that nitrogen, right. That may be true if you have a C2 axis through these two nitrogens, but then these carbons will not find a partner. And for those who might be wondering what we are talking about, in case you need, we are talking about symmetry of the molecule, and we have a prior NPTEL course on symmetry in chemistry. Those lectures are freely available on YouTube. In case you need help, you can refer to them. Okay, so this has a C2H symmetry. We will mention to the, we will refer to the C2H symmetry in passing a little later. So, this is something that was known for a long time, almost as long as the 3-hydroxyflavone case that we discussed earlier, that you have this dimer, you excite it, and then when you excite, remember, organic acids become stronger acids in excited state. This NH is an organic acid, this nitrogen in the 5-membered ring is an organic base, bases become stronger bases, and therefore, there is a double proton transfer. This was known very well. I am going to show you the spectra. It was manifested amply in the spectrum, and the energy surfaces were also worked out, and the energy surfaces is qualitatively same as that what we had for 3-hydroxyflavone. Asymmetric double well potentials in ground and excited state with a reversed asymmetry between them. Okay. The state that is more stable in the ground state, let us say the form that is more stable in the ground state is less stable in the excited state. That is why proton transfer takes place in the excited state, and since two protons are getting transferred, it is called excited state intermolecular double proton transfer. In our lab, we have done some study on another molecule which we call BPOH2. there we have excited state intramolecular double proton transfer. And it is manifested in the steady state spectra, as I told you, like this. Okay. These are the absorption and emission spectra at different concentration of 7-aziendole. Do not think that dimers are formed at very low concentration, they are not. In fact, even for 10 to the power minus 4 molar concentrations, which is pretty high for fluorescence, you do not get dimers. Okay. In absorption, you see there is a little bit of change. This one, the blue one is monomer, and the other one, which color is it, green or red? Red. The red one is for dimer. So, as concentration increases from 10 to the power minus 4 molar to 10 to the power minus 2 molar, the absorption changes a little bit, there is a little bit of redshift and the structure also changes. But you get more drastic changes in the emission spectrum. This is the monomer emission spectrum between 300 and 400 nanometer, and you see it is more or less mirror image of the absorption spectrum. Okay. And these spectra are all I think normalized to this peak. As concentration increases, what you see is in this 400 nanometer to 700 nanometer region, at 10 to the power minus 4 molar, there is hardly anything. Actually, something is there, but you see it only when you draw a semi-log plot. And as the concentration increases, I look for the C2 axis later, it is not there. As concentration increases, the Stokes shifted band characteristic of excited state process keeps on increasing. That is why the primary assignment of this to the excited state process happening in dimer was done, right. So, this is something that was known, and even reaching there actually was not easy. The reason why this debate started in 1998 and not in 1978 is that people had to characterize, people had to say with confidence that this is a dimer. So, several kinds of studies had to be done, mass spectroscopy and so on and so forth. They had to be confident that excited state double proton transfer is taking place. A lot of studies were already there before the debate broke out. So, what was the debate? That is what we will take in the next module.